On behalf of RBCS and Software Test Professionals, we welcome everyone today to this webinar on listening to your defects. I'm Rex Black, President of RBCS, a worldwide testing and quality assurance firm serving clients ranging from small startups to Fortune 20 global enterprises. Since 1994, RBCS has been both a pioneer and leader in quality hardware and software testing. RBCS has offices in the United States with partners around the world. RBCS delivers insight and confidence to our clients, helping them get quality software and hardware products to market on time and with a measurable return on investment. We have a team of international consultants that deliver customized training, consulting, and outsourcing services for companies that are looking to improve their testing and quality assurance practices. We've helped hundreds of companies reduce development and support costs while assuring the best quality products are delivered to their customers. I'm the author of Pragmatic Software Testing, Advanced Software Testing Volumes 1, 2, and 3, Foundations of Software Testing, Critical Testing Processes, Managing the Testing Process, and Fundamentos de Pruebas de Software, first book on the ISTQB certification in Spanish, and the first book in any language aligned with the 2011 Foundation syllabus. I have a degree in Computer Science and Engineering from UCLA, and I am the past president of the International Software Testing Qualification Board and the American Software Testing Qualification Board. RBCS presents this webinar in partnership with Software Test Professionals. If you haven't visited their association website, make sure you check it out. That's www.softwaretestpro.com. I was a keynote speaker at their recent conference in Dallas. Thoroughly enjoyed it and actually gave this very presentation there. So if you missed it in Dallas, you can hear it today. Attendance at today's webinar earns PMI PDUs, and I would like to thank Rex Price for reviewing the material for PDU status. Visit www.pmi.org to claim the PDUs using code LTD100. That's PMI PDU code LTD100. Before we start the presentation, a couple of housekeeping notes. If you have any questions during the course of the webinar, please feel free to submit them throughout the presentation via your webinar interface. Please note that I only check them at the end, though, so I cannot monitor the questions throughout. There will be a question and answer session at the end where I will go through all of those. There is no need to ask for presentation copies. The presentation is posted on the web, www.rbcs-us.com. Go to the basic library page. Towards the bottom of the page, you will find the PDF version of the slides. You also do not need to ask about how to register for the free e-learning. Just by attending this webinar, you have automatically registered. Check your email over the next couple days and watch the spam filter to make sure that the notification doesn't get lost there. You do have a limited time to respond if you are the winner. Realistically, given the Thanksgiving holiday here, the notification may not go out until Monday, but we might get it out tomorrow. If you are having problems with the audio or visual components of the webinar, please contact GoToWebinar support. If you cannot get to the webinar online, or if you're dealing with an unreliable connection, please download the slides. As I said, they're on the basic library, www.rbcs-us.com. Go to the Resources tab and select Basic Library from there. And use telephone to connect rather than voice over IP. We do occasionally hear of various sorts of glitches that people have. There does seem to be some sensitivity to settings and browsers and so forth. And apologies on behalf of Citrix if that happens to you. Trying another browser is, if you're having difficulty, often the quickest way to fix the problem. I hope you enjoy this free webinar from RBCS. We do these free webinars as a service to the software testing community because at RBCS we're a not just for profit company. And today's presentation is on listening to your defects. Defects can tell you a lot about what's going on. And we'll talk about how to manage testing more effectively by listening to what your bugs have to tell you. Might not all be as obstreperous as this fellow here, Cicada, if you recognize him, but if you listen carefully, they have a lot to tell you. I like this quote from Yogi Berra. Like a lot of his quotes is simultaneously silly and profound. Not sure how he managed that, but you can observe a lot just by watching. Yes, indeed, and also by listening you can. So we listen to our defects. What can they tell us about? Well, they tell us about what's going on in our projects. They tell us about the state of our products. They tell us about how the process is working. So in the next few pages, we'll look at what defects can tell you about those three areas, and also things to watch out for. Just make sure you don't hear what they're not telling you. Okay, so fairly typical in testing to have some sort of exit criteria, and often this will relate to release criteria related to defects, remaining defects. So this is a project-related criteria that we're looking at here, project-related measurement that we're taking. So there's a couple things that are involved. One of these criteria is, are we done finding bugs? Or are we still finding them? Because if we are still finding bugs and testing, we're probably not ready to call the project done. And have all the important bugs been resolved? Because if there are still pending bugs, then waiting to be fixed, then that's likely to hold up our release until those get fixed. So we want to monitor this with defect data as the project continues. Now, one thing I'll point out here, I'll show you in a minute how you might do that. I'll mention, though, that these charts, or this chart that I'm about to show you, does depend on timely entry of defect data. If the data is not kept up to date, bugs aren't entered until well after they're found, status isn't updated when bugs are fixed, this chart will get very noisy, and you won't get accurate information out of it. Basically, your bugs can only tell you what people put into them, and if the data is not accurate, the data is not timely, then its reports will not have the same level of informative value. Okay, so some of you might have seen this chart before if you've seen some of my other presentations on metrics. Let me go through this here. Let's see. How do I want to do this? Spotlighter. Okay, I want to point certain things out. So there are 5 data sets that are graphed on this chart. Now this chart, it's a trend chart. So it runs, the x-axis here is time, and it runs from the starting of testing to the planned project end date of March 21st. We have 2 axes here. We've got this one, this axis, and notice that we've predicted that integration and system testing will find 2,000 defects by the planned project end date. So we have a predicted number of defects there. That's where we expect the total number of defects to converge. Then the other axis is over here, and that's exactly 1/10, as you can see, of this one, just to make it kind of easier to refer to and read. So 5 data sets being graphed. The first one is the total daily open. That's this red line. So the cumulative number of defect reports that have been submitted. And notice that we've got some indications on the graph of why it's kind of bumpy and not smooth, like the Thanksgiving holiday here, and then you do heavy exploratory testing on Friday, leading to a jump in bugs, as explained here. Okay, now the second data point is this green line here. This is the total daily closed including deferred bugs. They're closed in the sense that they are no longer an issue for this project. These 2 data sets are graphed against this axis here, so we've got at this point somewhere around 1,200 bugs that have been found, and somewhere under, it's probably more like 1,100 bugs that have been found, somewhere under 1,000 bugs that have been fixed. Now, notice you get this notation here, confirmation testing of the fixed bugs makes the total close curve jump on Mondays and Tuesdays. Do our confirmation testing when we get the new releases every Monday morning. Okay, so what do we want to happen with this? Well, we've predicted 2,000 total bugs, so we would expect that this would go up and then kind of level off and converge right around 2,000. That's one of the things we want. So when I say level off, I mean it would be flat, and our defect find rate for the last week or so would be 0, we hope. And this total daily closed should converge with that somewhere right before the planned project ship date. So we are actually finished. Finished fixing bugs, finished confirmation testing the fixes, finished finding new bugs. So from a defect point of view, no further project impediments. Now, to the 3 other data sets. The minuses, the average daily opened here, the way that's calculated is you add up the number of defect reports that are filed in a week, divide by 7. That's the average number of defect reports per day. The pluses are the average daily closed. So similarly, you add up the number of defect reports that are closed, divided in a week, divided by 7. That's the average for that week. These are graphed against this axis over here, which is kind of explains why they could be so prominent in respect to these totals. So basically what you want to do is look at the relationship between the plus and the minus, and the plus is well above the minus. It's a good week because you close the backlog. The minus is above the plus, then it's not such a good week because the backlog opened up further, which we don't like, right? That's not a big backlog poses a number of risks to the project. Duplication of defect reports goes up. The ability of the developers to actually replicate the failure goes down because the time elapsed between the location of the bug and the developer actually trying to isolate the bug and fix it often is long enough that the behavior of the system changes, and the exact steps to reproduce might not look the same way or result in the same behavior. So that ends up defect reports being kicked back to the developer, the tester, saying, please try this again. And the closure period, the duration of the defect reports and how long they're open tends to go up as the backlog goes up too, of course. So that means that that's increasing the risk of project delay. So because backlog is a problem, I have shown the average daily backlog here as these orange asterisks. Now that's calculated by taking the daily opened, this one, subtracting the daily closed for each day. That's the backlog on any given day. And you add that up over the week and divide by 7, and that's the average daily backlog. And what we see here is the backlog really, it was going up in a somewhat alarming rate, and then it got really alarming here in the November time period, and it's reached almost a crisis level, in my opinion, in this mid-December time frame. And it is starting to come back down, but still is a very large number and certainly a source of concern. So on this project, the defects are basically telling us that while we seem to be more or less on track to find the predicted number of bugs, and are apparently progressing through our testing from a point of view of finding bugs we are taking some risk with the fixed time, and something needs to be done to try to accelerate that. Okay, so this project. How about product? What's the state of our product? Can defects tell us something about that? Well, they can. Tell you about what the residual level of quality risk is, and also where defect clusters might exist, where there are proportionally larger numbers of bugs. Now, these charts that I'll show you in a minute, what can we do with them? Why do we want them? Well, we can make smarter release decisions if we are aware of the remaining level of quality risk. So I'm going to be able to tell managers, this is the risk that you would be taking by releasing the product now. And do we want to do that? Also, we can make product improvement decisions with the defect clusters by saying, there's some areas of the system that are really very buggy and need to be cleaned up. So let's look at this chart. Now, this chart came from an article that I wrote with Tsushi Nagata of Sony. So we worked with Sony to help them introduce risk-based testing into their organization, and they've done that, and that's that's gone reasonably well. But they also want to have risk-based results reporting. Nagata and I were working on how to present this information, the residual level of risk, in a way that would be most accessible and most informative to the Sony managers. And this is what we came up with. This article is now posted on the RBCS website. I believe it's either the articles page or the basic library. It was in the most recent newsletter too, which went out, so you can find it there. So if you want to read the whole article, how we came up with this and the evolution of risk-based testing, risk-based results reporting, you can read it there. Let me explain the graph. Okay, so we have the residual rate here. Okay, and we're graphing two things here. We're graphing our progress through the test cases. That's this blue curve. You notice that the blue curve goes from 100%, so there's 100% of the tests remain to be run. So that's the residual test cases. Okay. Residual meaning at this point what remains to be run. Down to 0%. This X factory, this is the planned product ship date. Okay. So we have a plan to run through 100% of the test cases here from the start of testing down to the release time. Okay, and this is test execution time here. Now, the ideal case from a residual quality risk perspective is that the risk curve drops off very quickly. And then kind of flattens out here. And you might say, well, why does it do that? Well, it does that because when you're doing risk-based testing, you do a couple things. One is you allocate test effort based on risk, and another is that you run the tests in risk orders. The higher risk tests are run earlier, which means that if you have a metric for what the remaining level of risk is, because you're running the tests that have the highest amount of risk earlier, that metric falls off fairly quickly at the beginning as you run those very high-risk tests, and then gradually levels off as you get to the lower-risk tests. Now, you might say, well, how come it doesn't get to 0? Well, there is a minimum level of risk that will exist, because while running tests allows us to reduce the likelihood of an undiscovered failure relative to those tests in those risk areas, the impact that would be associated with a potential failure there remains the same. So you cannot reduce risk to the quality of the system to 0 by running tests. So this is the ideal. Now let's look at what happened with the actual here in this on this project. The actual is well above the ideal and even above the test cases. So the rate of risk reduction is actually less than the rate of running test cases. Why is that? Well, because some of the critical features that were associated with the higher levels of risk were not delivered in early versions, and so the tests that could be run ended up being tests that were relatively lower risk. Now, at some point, we see that this does start to drop down fairly rapidly as the critical functionality is available. Eventually, it almost connects to the residual test cases here, but then they'll run into some additional blockages and other issues that prevent the risk from going down. It's bugs that remain unresolved, for example. So we get to the planned ship date and we say, okay, here's some residual risk that remains from the minimum case to what's actually here. And that can be reported in detail in terms of the tests that fail and the bugs that remain to be fixed. Also, it can be tests that did not get run, but in this case, all the tests did get run. Now, if you're curious about this, as I said, you can read the article, which is posted on the website. Now, if you're saying, geez, this is the first I've ever heard of risk-based testing, this sounds really interesting, what do I do? Where do I get more information? What you might want to do is go out to the digital library. So that's the rbcs-us.com webpage. Go to the resources page, navigate to the digital library. We've got a whole bunch of videos out there of presentations that I've given on risk-based testing, and can use those to get a better sense of what risk-based testing is about. There's also a recorded 2.5-hour presentation, videotape presentation that you can get. That's on the RBCS store that will explain more about this. So, bug clusters. How do we find the bug clusters? Well, this chart shows us that. This is from a project where we did the testing for one of our clients, these are the major components of the system here. We had 1, 2, 3, 4, 5, 6, 7, 12 components total. And what you're seeing here is this is bug clustering. There's not the bugs are not evenly and randomly distributed throughout the product. They tend to be clustered. And what you see is often a situation like one shown here. So we have 3 out of the 12 components, or 25% of the components. Between them account for 69% of the defects, the bugs. That's a fairly typical thing. You would find that's radical inequality, if you will. And also the difference between the components that have the bug clusters and the ones that do not is very clear, right? You see this dramatic drop-off. So 19% of the defects are in email, and then the next most important contributor, the WMAL, that's only 10% of the defects there, so it's less than half. Or about half. We see you got 28% and then 22%, 19%, all fairly consistently large numbers for this OSS browser and email components. So it really kind of pinpoints the defect clusters and allows us to say, okay, this is where the product is particularly weak from a quality point of view. This type of chart, by the way, is called a Pareto chart, and is very useful for doing this kind of causal analysis. If you're not familiar with how Pareto charts are created and what they can be used for, I encourage you to do a little web research on it, because it's a very powerful tool in the arsenal. Okay, so we can also use defects to find out what's going on with our process. Now, when I'm talking about process, I'm talking here about the software engineering process. And it's primarily a human process still, much more so than other forms of engineering. I think if you think of say a civil engineer making a bridge, obviously there's human labor involved in that process, but a lot of standardized components, and there's mathematical formulas that determine how the bridge behaves and the components in the bridge behave and so forth. So it's a much more automated and mathematical kind of process. Software engineering, we're still in terms of where we are as an engineering discipline, we're basically about where the Romans were with respect to civil engineering. We can make stuff, and some of that stuff is pretty, and some of that stuff is useful and will last some amount of time. But we're certainly not engineering it in the same way that a civil engineer builds a bridge, or a aeronautical engineer builds an airplane. We have some ways to go there. So software engineering, very human process, and any human process is fallible. The more of the human ingredient you have, the more fallibility you get, and it's not always the most predictable kind of fallibility. One of the things that you'd want to look at, one of the things that a number of our clients want to look at, is what's the cost of these mistakes? So how much is the fallibility costing us, and what is our quality capability right now of our process, software engineering process, and what improvements could be made? So cost of quality is a technique that can be used to look at this. Very powerful technique. I'm going to show you an example of that. We used this technique, cost of quality, earlier this year for a client, and managed to locate somewhere between $100 million and $250 million in cost of excess failure. I say excess failure, I mean they were paying more to deal with defects than they really had to, based on their level of defects, mostly just by letting them get so far along in the process that they were very expensive to calculate. Obviously, that kind of money is something that gets people's attention. And I'm sorry, I misspoke a moment ago. I said they let the defects get so far along in the process they were difficult to calculate. What I meant to say was they were difficult to, or expensive to remove. So how does this technique work? Well, it's actually fairly straightforward. It's a simple mathematical technique. Excuse me. What we're looking at is the value and efficiency of the process, basically the software engineering process. And what we're going to do is, in cost of quality, is we're going to say, on a project, there are various costs, right? Anytime you're doing a project or you're creating a product, there are costs associated with that. Some of those costs have nothing to do with quality, but there are 4 types of costs that do affect or do relate to quality. One is cost of prevention. This is money that you spend to try to prevent defects from happening. So, for example, if you train the developers to write more maintainable and secure code, that's a cost of prevention. Cost of detection is the money that you spend on testing that you would have to spend even if you found no defects. So, setting up the test environments, writing the test plan, doing the quality risk analysis if you're doing risk-based testing, all of those are the costs of detection. Now, cost of internal failure, these are the costs that you incur when defects are found, often by testing, prior to release. So the cost of internal failure would be the filing of the bug report, the fixing of the bug, the return of the fix back to the tester for a confirmation test, the run of the confirmation test by the tester, the run of regression tests by the tester to see if the fix broke something else. Those would all be costs of internal failure. So notice that the testing budget, part of the testing budget is cost of detection. The other part is a portion of the cost of internal failure. The last of the 4 quality costs is cost of external failure. This is what you pay when you don't detect all the defects prior to release, and some of them end up going out into production, out to the customers. Now, typically what you find when we quantified this with clients or other people quantify it and let us know about this, you find that the cost of external failure on a per bug basis is significantly higher than the cost of detection and internal failure on a per bug basis. So you save a considerable amount of money. We can calculate the testing return on investment using those figures. Let's take a look at an example. Now this example and how exactly it was calculated is described in detail on the article on the RBCS website as well. It's, I believe it's either the basic library or the articles page. It's called Testing ROI, and describe exactly how this is calculated. Let me get a highlighter up here so I can walk you through this. Okay, so what we're going to do here is for a project that my associates and I did for a client when we did the testing, we're going to calculate the cost of quality and how the different quality costs really, and how those relate to the return on investment in testing. So we have a testing budget of $1 million on this project, and that's how much was spent by the client for the testing work of the about 9 months that the testing went on. Now, out of that, there was about $100,000 that was invested in creating tools and environments and so forth that would be reusable on future projects. Those quality costs really, or those costs really need to be removed from the equation or amortized to some extent. So basically what I assumed was that 10% of the testing budget was creating stuff that would be used over a large number of future projects. So I pulled that out. You might choose not to do that if you do this calculation. You might leave that in. Now, retest costs. These are confirmation test and regression test costs associated with bug fixes and new releases. So as such, these are costs of internal failure and thus have to be accounted for somewhere else, because what I'm accounting for here is detection costs. So I'm going to pull those out and put them somewhere else. So $1 million minus $600,000 is $400,000. This is what we spent on testing for that project alone that we would have had to spend even if we hadn't found any bugs. We did find bugs. We found 1,500 must-fix bugs. So the average cost of detection per bug is $400,000 divided by 1,500, which is $267 per bug. That's average cost of detection per bug. Now, internal failure costs, retest costs, that's the money from up here. I've just pulled it in and dropped it down there. Test bug fix costs. These are the costs that the developers incurred in fixing the bugs. And I just calculated this based on the number of developers that were assigned, typical salaries for developers, and they were assigned during system test when the system was feature complete. So basically what they were doing was fixing bugs. So the average internal failure cost would be this plus that. Excuse me, the net internal failure cost would be this plus that. 1.25 million. So I divide that by 1,500 and I get 833. That's the average internal failure cost per bug. So if I add these two together, 267, 833, I get 1,100. So the cost to find and fix a bug prior to release is $1,100. So how does that compare to the cost of dealing with the bug post-release? Well, let's see. So there were $3 million in sustaining costs incurred in the first 6 months after release. Now, why did I take the first 6 months as the period? Well, the product continued to evolve and new features were added and so forth. So really, after 6 months, it kind of wasn't the same product that we had tested before. So it didn't seem right to claim more of that cost. My return on investment would have looked better if I'd included it and run it out for a year or so, because the overall sustaining costs would be higher. But it didn't seem right to do that, so I wanted to keep this business case conservative. So yeah, $3 million of sustaining costs. According to the folks involved in the sustaining, about 50% of that was bug-related effort. The other 50% was adding new features. So 50% of $3 million is $1.5 million. That's the net external failure costs. There were 500 must-fix bugs that were found after release in that first 6 months. So our average external failure cost per bug is $3,000. So in other words, every bug that we find and fix in testing saves $1,900. That's $3,000 minus $1,100. There were 1,500 must-fix bugs found in testing, so 1,500 times 1,900 gives you 2.85 million. That's the net benefit of testing. Now, if you take that and divide it by the net detection costs, you get the return on investment, 713%. Now, some people would say, well, you really shouldn't use the net detection costs, you should use the entire budget of testing. I'd say, I don't think that's quite right, because that includes internal failure costs, and those are not, that's not associated with my efficiency from testing point of view. It's associated with the inefficiency of the development process, right? Because the internal failure costs go up the more the bugs are delivered to testing by the developers. So it seems like you're not measuring the right thing if you include the entire budget there. So the net detection cost would be what I would use. So 713% return on investment, pretty good return. That's basically every dollar spent on testing saves $7 in the long run. So, and that's, you might ask, well, is that usual? Is that very high? Actually, that seems to be about typical. There's a wide range that we've seen with our clients when we do assessments on this. There was a study done by a fellow named David Rico for the Defense Department. He looked at various software process improvements, and he found that testing on average had an 800% return on investment. So this seems to be sort of right in that range. Okay, so we looked at various ways of listening to your defects and getting good information about your product, process, and project. But, pardon me, there are ways of mishearing what your defects are telling you, and this does happen. We've seen examples of it. One is you reward or punish people based on bugs. This is going to very badly skew the numbers. So, for example, we heard a anecdote from a client in an assessment earlier this year. They were talking about performance evaluations and annual performance evaluations. And for the developers in this one group, they had a objective that was set in their yearly performance evaluations that was measured against, and that objective was that they could not have more than 2 severity 1 defects filed against their code in the course of the year. Now, laudable intention there of getting developers to think about quality and be careful as they write the code. So, yeah, intention's good, results bad. Because here's what happens with that. The developers, once they got to their second severity 2 defect, would start to just beg the testers not to report defects as severity 1s, but rather to deflate their severity, to report them as severity 2s. The dialogue would go something like this, that the tester would find a bug and call up the developer and say, I found this bug in your code, and it's it's a severity 1 bug because it meets the criteria for that. And the developer would basically say, oh no, please don't throw me in the briar patch here. I'm going to be killed by this if you you report this as a Sev 1. Please report it as a Sev 2, and I swear I'll fix it. It's going to get fixed. I'm not going to try to get it deferred, but I'm going to get dinged on my performance evaluation if you put that in there as a set of 1. So that the poor tester is caught in this bind, right? It's like, okay, well, either I put in data that I know to be incorrect into the bug tracking system and corrupt my process metrics in so doing, basically, as well as subverting the bug management process, or I get a colleague of mine in trouble, and that colleague, of course, might be in a position to take some amount of revenge for that, which puts the tester in a tight spot. So this is classic example of that. Well, you might say, okay, well, we won't punish, we'll reward. How's that? We'll reward testers for finding more bugs, as we want to find defects, and that seems reasonable, and reasonable enough that it seems like most test teams that have been in existence for any length of time have tried that at least once in some form or another, either putting a target in someone's annual performance evaluation, or actually giving bonuses based on the number of bugs found, or some other thing. And what ends up happening is, again, more data corruption. It's an incentive to report a bug, and then of course people report bugs. And because simpler bugs are easier to report, people will focus on reporting the simpler stuff, like, oh, there's a misspelling on this screen, and there's a misalignment of a field on that screen, and they just go through and just nitpick the system like crazy. And the more important bugs, which are harder to chase down, the ones like reliability problems and so forth, it could take an hour or 2 hours, 3 hours to properly isolate the defect and report it. Those don't get reported. So you end up having exactly the wrong result out of this process, which is that people are pointed towards finding less important bugs and away from the more important ones. And the developers, of course, are deluged by this tsunami of mostly trivial bug reports. And of course, they hate it, and they stop taking the bug reports seriously, because they just start thinking, well, this is just a way that testers use to get bonuses. So it's all noise. And having once done that, it's very difficult to undo that impression. We did an assessment once where a previous test manager, 5 years prior, had a program like that for about a year before he was let go and replaced by somebody else. So it'd been more than 5 years since anybody had been in any way incented to report a bug. But still, the oral tradition amongst the developers was, yeah, the testers get incented to report bugs. They get bonuses based on the number of bugs reported, and they still had a great deal of skepticism about the bug data because of this. So that's a real problem of basically you corrupt the data by giving someone the wrong incentive, the wrong nudge, if you will, to use the current popular term. Another thing that's important is that you have to understand that just in general, it's a big risk to use process metrics for people metrics. And if you're measuring a process, you might say, well, it's software engineering is a human process, as I said before, so certainly the people are a very important factor in the process, and that's true, they are, but they're not the only factor, and there tend to be a lot of other factors that are moving the process along. This could be a whole separate discussion about this problem, because it is such a famous one, but I would just refer you to the internet and take a look at Deming's red bead experiment, it's called, which is about the problems associated with mistaking a process metric for a people metric, and rewarding and punishing people based on process metrics. Now, here's an example of mishearing defect data, or failing to really listen to it. So one of our clients does industrial control software, industrial control systems, runs things like oil refineries and pharmaceutical plants and stuff like that, stuff that, you really do want this stuff to work. You do care that the drugs you take are properly formulated, and you do not want oil refineries to blow up. That's a bad thing. So they test these systems. They're complex industrial control, real-time systems, as they need to be good. So we found during an assessment, going through their data, that they had a very large percentage of bad bug reports, basically bug reports that were rejected as not being actual defects. So I asked people outside of the test team why they thought that was. Well, why do you think there are so many bad bug reports? And it was a large number. It was like in the 25% range or so, which is well above the target we usually set for, like, in an assessment. 5% is the sort of threshold of where the number of bad bug reports, false positives, basically becomes an issue. So we asked people, why do you think that's happening? And almost to a person, the response was, well, the testers don't have enough experience with using these systems in a real-world setting. They've never worked in a pharmaceutical plant. They've never worked in an oil refinery. Or they haven't done enough work there. They have insufficient real-world experience to be able to recognize what would actually be problematic behavior. Now, this sounds very reasonable, given complex systems. And of course, if you've ever been involved in testing complex systems, you know how important domain knowledge is, the understanding of the business problem to be solved. So this does sound quite reasonable. But to avoid jumping to conclusions, I wanted to do a test with the defect data. So what I did was I asked the test manager to give me the defect data broken down by the percentage of defect reports rejected by person and the number of years of plant or industry experience that tester had. Didn't need their name. I just needed those two things: number of years of experience and the percentage of reports that were rejected that they had filed. And got that data, created a scatter plot, as you can see here. And this is another very useful tool. If you're not familiar with how to use scatter plots, I'd say go out and do a little internet research on that. Very, very useful thing, because what the scatter plot allows you to do is check to see if there's any correlation between two factors. And in this case, what we were looking for was a strong correlation between the years of experience and the percentage of defect reports that would be rejected. And it should be, if there had been a strong correlation, what you would have seen is a very clear high number of rejected defect reports over here, and then a line just like going down like this. Instead, what you see, I drew the trend line here. Okay, and that's not. It's going down, but not by much. And more importantly is this R-squared value, which shows the degree of correlation. And an R-squared value that's close to 1 indicates high correlation, and an R-squared value that's close to 0 indicates very low correlation. And so what you see here is actually very low correlation there. So clearly there's something else going on above and beyond the number of years of experience that the testers have. So, when you're listening to your data, really do listen to your data. If somebody's saying, well, the data is telling me this, then check it out. Okay. Get this back in a normal mode here. So, what do you got to do to listen to your defects, to listen to your bugs? Well, obviously enough, you got to log them. You got to put them into some sort of tracking system, something that is accessible to the people who are reporting the defects, easily accessible to them ideally, that they understand how to use. The defects need to have classification information associated with them. So things like, what subsystem were they in? Where was the defect introduced? Where was it detected? Where was it removed? So you can look at things like what's called phase containment. What's the number of defects escaping from one phase to the next? The data needs to be kept clean. I mentioned this client before where we had found that they had somewhere between $100 million and $250 million in waste, excess failure costs. And that, by the way, was on a $1 billion annual IT budget, so it was anywhere from 10 to 25% of their total IT budget was being wasted on dealing with defects. Now, you might say, well, how is it that you couldn't tell whether it was 100 million or 250 million? Well, it was because the data was dirty. More importantly, the data was so dirty that we couldn't even make any solid recommendations of how they could go about reducing that cost because it was so noisy that you couldn't figure out which were the more important process issues resulting in a high level of defects and which were less important. The analogy that I used to explain that to them was, imagine that you're standing in front of a table. The table is covered with money, and on one side of the pile of money is predominantly $1 bills. On the other side of the pile of money is predominantly $100 bills. And I tell you to go ahead and stick your hand into the pile wherever you like and grab as much money as you can in one hand and walk out the door. And what would you do? And they said, well, of course you stick your hand into the part of the pile that has the $100 bills in it. I said, right. But imagine this. Imagine that we're standing outside of this room. I explained the situation, that there's a table inside with a pile of money on it, and it's got predominantly $1 bills on one side of the pile and $100 bills on the other side of the pile. And I explained to you that you'll be able to go in and stick your hand into the pile wherever you choose and take away as much money as you can hold in one hand. And then before I take you into the room, I blindfold you, and when I stand you in front of the pile of money, I don't tell you which end is which. And I said, that's the exact situation that you find yourself in now. You know you're in front of a big pile of money, somewhere between $100 million and $250 million, but you don't know if you start making changes whether you're sticking your hand into the $1 side of the pile or the $100 side of the pile. So it is really important to keep the data clean, because if you want to make long-term process improvement decisions, you want those to be based on reliable data, not just gut feel, because, as we saw a minute ago, what sounds reasonable, what the gut tells you can be wrong, and of course that's the most dangerous kind of wrong. A wrong that sounds reasonable is one that you might actually go along with. So, the situation with the testers, the less experienced testers filing more bad bug reports sounded very reasonable. Like, if I hadn't tested that out with that scatter plot, I could have made the recommendation in my report that they shouldn't hire people who have less than some X number of years of experience. Everybody would have agreed with it, probably would have implemented that recommendation, but it would turn out to have been wrong. So you need clean data to be able to make good decisions. And part of that is making sure that people have been trained in how to use these classifications. You set up these classification schemes for your defects. You need to make sure that people know how to use them. This turned out to be one of the big problems that our client had, was that they had not trained people in how to use the classifications. They had a sophisticated set of classifications that they were gathering for their defects, but hadn't trained people to do it. So one of the things that we spent a goodly part of the first few months of this year doing was running everybody in their IT organization, developers, programmers, business analysts, testers, designers, all of them, including their outsourced staff, through live and e-learning training on how to do these classifications, because they came to realize how important it was going to be to get this information solid. Okay, so some conclusions here. Defects can give us a lot of information about our projects, about products, about processes. I've just kind of highlighted some of them here. We did together with Core Magazine, a series of articles on metrics. Most of those are now posted on our website. The last one will be posted probably in the next couple months. And so if you want more examples of defect metrics and other metrics that relate to projects, products, and processes, then you can go find those on the website. Now, as I said, be very careful not to misinterpret what your defects are telling you. I gave you some examples of how that could happen, and it happens pretty frequently that people make mistakes with metrics. Sometimes people say, "Oh, well, because people make mistakes in metrics, we just shouldn't use metrics." That to me is like saying because people have car accidents, we shouldn't have cars. I mean, metrics are extremely useful in making fact-based decisions, objective decisions, rather than subjective emotional decisions. But they like a car, they have to be used with care to avoid damaging things. So, do it, but do it right. Now, when you do it, when you listen to your defects, this can help you make smarter decisions, optimize your outcomes, release decisions, process improvement decisions, product status decisions. All of those things are things that defects can help tell you. So if you haven't tried some of this stuff and some of these metrics, give it a shot when you get back to work. All of the spreadsheets that were used to generate the graphs that you saw today are out in the basic and advanced libraries on the RBCS website. And as I said, a number of those are described by articles that you can find there as well, so how to use them and so forth. And there's a lot in managing the testing process. The third edition has a lot on metrics. So does the Advanced Software Testing Volume 2, which is the book about test management. That has a lot on metrics as well. And my upcoming book, Expert Test Manager, will have quite a bit of coverage on metrics. Okay, so that winds up the presentation proper. We'll go ahead and put the advertisement up here on the screen while we take questions from the audience. Give me a moment while I undock the questions pane here from the GoToWebinar interface. Get this up and running here. Okay, got a question from Alexander relative to the first chart that we looked at, which was how can we predict the number of bugs to be found. So let's go back and look at that chart. Whoops, this one. Yeah, so Alexander is basically asking, how'd you do that? How'd you make that prediction? Okay, the way that you do that is by using historical data. There is a spreadsheet that's available out on the RBCS website. I think it's in the basic library. If you look under test estimation slot there, if you will, row in the table. It's organized by the various areas of the test process. So you look under test estimation part of the process. You can find this. I think it's called estimating bug find and fix, and you'll see how that kind of thing is done. And basically, what you do is you look at the average number of bugs that will be introduced on a project based on some sort of sizing metric of the project. And the three most common sizing metrics would be either new and changed lines of code, new and changed function points, or the number of programmer days or developer days that will be spent developing the code. Either one of those should be reasonably reliable. You calculate what that average is, and then when you're estimating your testing, you use that to predict the number of bugs based on what's true about this project. And you can even, if you've got good historical data from your defects, this is another thing that listing your defects can tell you. You can even predict how long it's going to take you to find and fix those defects, because you can make a predictive version of this chart that's shown here, and that'll allow you to predict your test end date with a fairly high degree of accuracy. We have some of our clients that are able to predict the number of bugs that they find to about plus or minus 20%, or better in some cases, and that allowing them to predict project end dates by about plus or minus 10% in a lot of cases. So, it's a powerful technique. Let's see. Oops. Excuse me. Okay, there we go. Let's see. The question from Aliona. Says, hi Rex, many thanks for the session. This is useful for traditional testing when testing is independent of development. How do you listen to defects when testing is done by developments? The same for the case when testing is done by customers or internal users, the latter being known as not always accurate at documenting bugs, and the former known for not documenting bugs at all. So what should we listen for in these cases? Well, yeah, I mean, this is the thing. You gotta log them. You gotta log them to listen to them. It's like if you have a thermometer in your backyard and you make a point of every morning going out and looking at that thermometer and writing down the temperature, and then every evening or mid-afternoon or whatever going out and looking at the thermometer and writing down the temperature, you can put that data in a spreadsheet, and you can show a graph of average high and low temperature on your, or not average, but daily high and low temperatures. And somebody asks you, well, what's the temperature likely to be on any particular day? You can refer back to what it was like last year and the year before and say, well, it's going to be likely to be like this. Now, of course, you don't actually have to do that, because you can just go online. Somebody else has captured that data somewhere and can make that prediction for you on weather.com or something like that. Without the data, you just don't know. So if it's not captured, that you just can't listen to it. So this is the thing, is that a lot of people talk about was, it's more efficient if we don't capture this and we just fix the bugs immediately, etc. Well, no, it's not more efficient, because it's not efficient to continue to do inefficient things, because you can't listen to your process and figure out how to become more efficient. So this whole argument that we can be more efficient by not logging defects just falls down on the face of it, because that's only true if there are no defect or quality related software process improvements that you need to make. In other words, you're from a quality and testing point of view, your software engineering process is already pretty much perfect. Since that's pretty much not true of anybody, then this argument of don't log bugs is really it just doesn't cut it for me. I have a question from Kathy here. When figuring the cost of quality, were the dollar amounts used just the budget and the cost for testing, or were developer dollars included in that? Yes, developer dollars were included. Let me go back and show you where they were included. Kathy, the developer dollars, sorry, I'm kind of struggling with this interface here, are in here, the bug fix costs. So that's their part of the internal failure costs, the money that they had to spend fixing the bugs, and that's what was included there. Let's see, got a question from Fred. What do you consider to be external bugs? Ones found in production or certification testing? Good question. Certainly ones found in production are external bugs. The question often comes up, well, what about UAT? What about user acceptance testing? Well, what about beta testing? The question there is was the purpose of that testing activity to find bugs or not. So, in a beta test, often one of the goals of a beta test is to find certain kinds of defects. And so that's actually just part of the deliberate defect detection that goes on, and those bugs would be a cost of internal failure. If the purpose of the testing phase or testing activity, user acceptance test or whatever, was not to find defects but purely to build confidence, then those would be basically external failures. Now this gets a little complicated when you have user acceptance testing going on in parallel with, say, system testing or system integration testing, because you can't, if you're testing the same products, it's not reasonable to have one test activity going on where you are deliberately trying to find bugs and another test activity going on where you expect not to find bugs. That's not connected to reality. So if the product has not been determined to be done using kind of analysis that I showed earlier, then it's not quite right to be running tests and saying, well, we shouldn't be finding bugs in these. I bring that up just because that literally happened with one of our clients where they had excuse me, they had user acceptance testing running in parallel with system testing because they wanted to get the system into production faster. And then they were going back and yelling at the testers saying, well, we're finding too many bugs in this. Well, for one thing, of course, it's not as if the testers put the bugs in there. So you're kind of yelling at the wrong person if you're yelling at someone about, there's too many bugs in this code, if you're yelling at a tester. The other thing that was ludicrous about it, though, was, well, of course there are still bugs in there because it's still being tested. I mean, there's still a test activity underway where the very goal is to find bugs, and they are still continuing to find bugs. So sorry to make what was probably, you intended to be a rather simple question, Fred, into something more complicated, but I wanted to be complete about this because it is something that does get screwed up sometimes. Let's see. A question from Aaron here saying, I cannot locate these slides on your website. Are they saved under a name other than Listen to Your Defects? So they should be saved under the name Listen to Your Defects on the basic library. If you still can't find them, send an email to info@rbcs-us.com. It is possible that in the run-up to this holiday, together with me being out of town for a month, that we kind of dropped the ball on posting these, but they're usually posted about a week before. Now, Todd asks, how do you generate the ideal curve related to quality risks? Okay, good question, Todd. Let's go back and look at that. Now, a detailed answer to this question, I'd refer you to the article, which, as I said, is posted on the RBCS website, as having to do with quality risk, and was mentioned in our most recent newsletter. So if you're a newsletter recipient, you've got the link to the article already in your inbox somewhere. But basically, what's happening is that there's what's called a risk priority number associated with each test case, and it's based on the risks, the likelihood and impact of associated with the risk that test case covers. And then there's also a risk priority number associated with each risk, which is again based on the likelihood and impact. So what happens is you start running the tests in risk-based testing. The tests with the higher level risk will be run earlier, as I mentioned. And so what happens is the number of remaining risk points, if you will, which can be calculated from this risk priority number, the number of remaining risk points goes down. Now that happens anytime you run tests, but the thing is that the risk points associated with the tests run earlier will be higher than the number of risk points associated with the tests run later. So that's why you get this sort of parabolic kind of curve where it's not really parabolic, I guess it's logarithmic kind of curve, where it's dropping off fairly dramatically at first and then less and less, because the tests that you're running towards the end ideally would be the tests that would have a fairly low level of risk associated with them. And the risk reduction power of each test is lower than was the case earlier. As I said, a detailed description of the chart and how Nagata and I came up with it is found in the article, and I would encourage you to take a look at that. Okay, we got a question from Dave. What about use of screen captures? I'm a firm believer of using screenshots along with text to describe the problem. Do you promote the use of screenshots? So as part of a defect report, yeah, absolutely. I mean, I think that can be very helpful. Screenshots, video captures, there are various utilities that allow you to do this. Any information that you can give to the developer that allows the developer to make more informed and efficient decisions about where to go looking for the bugs and what to try first is I think very helpful. So yeah, I would say you should do that. And you want to set up your system such that it can support that. Okay, so some email questions here. One of which I already partly answered. We're working on an agile project, and we don't track bugs that are fixed in the sprints. We only track bugs that are fixed if they're fixed in the later sprint. What does this mean in terms of our ability to listen to bugs? Well, related to my comment earlier, this obviously imposes an enormous blind spot. And again, if you don't track it, you can't measure it. You don't have data. Now I know what happens when if you bring this up. What you're likely to hear is what I often hear when I make this statement about you need to track bugs found throughout the development life cycle, including in Agile during the sprints. And then people say, well, that's not Agile. Well, okay. I would say it's not Agile to use 3-word firing squads like this to shut down debate on important questions. That's not Agile. To tell someone, shut up, we can't talk about that because that's not consistent with the current prevailing beliefs about how Agile is done. That just doesn't strike me as very Agile. That strikes me as sort of willful, I'm not going to say willful ignorance, but it's like we refuse to debate this point because there's some theology or dogma out there. Let's have this debate. I would say that it is Agile in the truest and best meaning of the word, to be able to manage your processes, projects, and products from a position of wisdom and insight, informed by facts rather than opinions. There's nothing Agile about letting superstition and opinions guide what you think should be done. So now the other thing too that I would point out, when people say, well, we don't track bugs and during the sprints, well, you know what I've seen is that the testers actually are tracking bugs. They're just not doing it in a way that could be used for metrics. So they've got bugs documented in emails, or they've got bugs documented in Word documents or Excel spreadsheets. So there's all this data, but it's not in any way accessible. So the point here is, if the issue is bug tracking is too expensive and it imposes too much overhead, then I would say, well, fix what's wrong in your bug tracking such that it has too much overhead. Why does it have too much overhead? How could you make it more lightweight? Focus on solving the real problem rather than, to use the cliche, that's basically throwing the baby out with the bathwater. There's a tremendous amount of good information that can be gained by good defect data, but if it's not tracked, then you don't have it. So another email question here. We use Jira for tracking bugs. Is that a good system? I've yet to find people that are using Jira for bug tracking that are getting out of it what people are using systems that are actually tracked or actually designed for bug tracking it can get out of it. Jira is more, from what I can tell, just a trouble ticket tracker, and systems that are designed to be used for tracking bugs are going to do a better job. Now, that to say that it wouldn't be possible to, say, customize these trouble ticket systems in some way. Yeah, it could, but I mean, there's sort of a element of, how much effort do you want to expend trying to make something, make a tool do something it wasn't designed to do, rather than just use a tool that was designed to do the job. So no, that said, designed to do the job. I mean, there are a lot of bug tracking tools out there, and I can't say that I've ever seen one that I would consider perfect off the shelf. So there's certainly, even if you're using a bug tracking tool, you can count on having some amount of customization that needs to be done. Then finally, let's see, how important is training people to enter good bug data in terms of being able to listen to the data? As I said before, it's really critical in terms of you getting the data right. That was knowing the $1 bill side of the pile from the $100 bill side of the pile. So do make sure that that you get people trained, and that people have uniform understanding, and especially the classifications. I mean, it's the narrative fields, steps to reproduce, and that sort of thing. What will tend to happen is that because those are read by people, to the extent that they're not being used properly, consistently, et cetera, then they'll get feedback on that. But the classifications, sometimes people don't pay as much attention to the classifications, and so they get used in inconsistent ways, and the meaningfulness of the data is lost. And it's a shame to have a repository with enormous amounts of data in it, and then find out, well, it's actually mostly noise because nobody knew how to use it. A question from Mike Schultz. With multiple test fields and usually limited resources, is it wise to switch test focus upon high bug clustering, or is neglecting other untested fields a higher risk on quality? Okay, that is a great question. I'm glad you brought that up. So we go back to the clusters here. As you can see, these three clusters, these three components have the highest rate of defects, and you might say, oh, well, we should really focus on testing those. Well, basically, the likelihood of a defect, this is an element of risk. It's the technical element of risk, but the other thing is impact. And there could be other parts of the system where defects would be very high impact, and even if they're not very likely, we still have to test there. So this is all risk-based testing done properly is not, I mean, basically you're not talking about just doing some sort of geeky bug hunt where you go, okay, I'm going to use this chart to try to focus on finding as many defects as possible in the time available to me, because there are, as I said, business-related risks, impact issues that need to be considered, and that's something that is not shown in this chart. Now, I was talking to a client about this last week while I was in Beirut, and they were saying, well, couldn't you modify this chart so that it actually took that into account, for example, by looking at the business impact of defects and including that in the metric. So you got basically a risk-weighted version of this chart. I assume that could be done. I've never tried it. So, if somebody wants to experiment with it and let me know how that goes, I'd be very interested to hear about that. Let's see. A question from Perry. How do we provide evidence of the PDUs for attending this session? So as I mentioned at the outset, Perry, maybe you missed this. You need to go to pmi.org to claim the PDUs, and the code is LTD100. LTD, those are all capitals. Listen to defects, LTD100. And that should work. If you have further questions, send us an email, and we'll help you out with that. Yeah, Mike's follow-up question. I guess by multiplying your bug amount by a certain risk factor, this could be assessed the business risk here. Yes, I think it could. As I said, I've not tried it. I don't want to say for sure that it would work without trying it, but if somebody wants to give it a try and let me know how that works, it would be that would be great. Okay, Perry says, thank you, LTD 100. Yes, that's right. Good luck with that. Let us know if you have questions. Oh, Mike says, will do. Thanks for answering. Okay, so go off and give it a shot. Create this chart, this bug cluster chart, and try to risk weight it. Let me know what you come up with. Maybe I'll post that out on the blog, and we can have a little discussion about that and pros and cons. Excuse me. Okay, well, that does it for this session. To close this out, let me tell you a little bit more about our resources available through RBCS. These free webinar sessions run at least once a month, so you can check our website, rbcs-us.com, to sign up. We will be doing 2 next month, actually. There's going to be a bonus webinar that's going to be presented in conjunction with SmartBear software on Agile testing opportunities. So I'd previously done a presentation called Agile Testing Challenges, and this recorded webinar that's out there. But wanted to give the other side of the coin and say these are the great things that come up in terms of Agile. If you would like a special webinar presentation for your company only of this webinar or on any other topic related to software testing, contact us at info@rbcs-us.com or via our website. A last minute question coming in here from Maria that I want to take. Defect cause analysis, could this be considered as part of the cost of prevention and cost of quality? Yes, if you're going to do defect cause analysis, try to institute process improvements and just any effort associated with process improvement in general. If that process improvement is focused on reducing the number of defects, that would indeed be a cost of prevention. Thanks for asking that, Maria. Now, if you don't already receive our regular free newsletter, you can sign up, rbcs-us.com. By signing up, you'll get valuable discounts on consulting and training services, along with a regular newsletter that includes a featured article on software testing and quality, like the article on risk-based test results reporting that was in the last issue. It's discussed here. The newsletter also contains news about what RBCS and its partners are doing lately. You can follow us on Twitter. We're at RBCS. On Facebook, we're RBCS-INC. Remember to check your email over the next few days. You might be the lucky winner of a free e-learning course from RBCS. You were registered for this random drawing simply by attending this free event. Check out my blog. That's rbcs-us.com/blog. Feel free to post comments. If you want to discuss a particular topic, send an email to info@rbcs-us.com and include the word blog in the subject line somewhere to make it clear you want to discuss the topic on the blog, and we'll get that up there. Finally, check out our digital library with recordings of these webinars, podcasts, and videos. You can subscribe to our podcasts via iTunes by entering RBCS Podcast into the store search string. That's free. You can see videos and recorded podcasts by subscribing to the RBCS channel on YouTube. That is also free. We offer these free resources as a service to the software testing community because at RBCS we are a not-just-for-profit company. This concludes the webinar. I'd like to thank everyone for joining us today. For those of you in the United States, have a great holiday weekend. Happy and pleasant Thanksgiving, and I'll hope to see you all back in the December webinars.